Go ahead.
Okay. So, or like Dr. Glean said, we'll be looking at the observables of photoluminescent charge transfer today, starting with charge transfer. One important physics concept related to that is the continuity equation. So, for a little context of where we're at, we talked about Redfield electron dynamic calculations last time. We did some calculations with those. One thing you can analyze with that is charge transfer, and we need the continuity equation, which is a description that pretty much tells us charge is conserved. So you've got local area, charge is moving around to a large area. Whatever charge there is has to be conserved. One way it generally gets described as the partial derivative of the charge density with respect to time added to the divergence of the current density. To adapt it to our model, we have when you look at a couple partial density distributions. So we have here on the bottom left the partial density distribution of our valence band, and on the right, or conduction band on the left, valence band on the right. Some items of note here, you'll see this in integration with respect to X and Y. To make our analysis simpler, we are just going to be looking across the Z dimensions, since it's easier to do some analysis looking at just with respect to one dimension and time variable. I suppose if you wanted to see how it looked in different dimensions, you could just turn your model around. But for my model, everything was one dimension Z, so it worked out. Or the way I expected the charge to transfer was in the Z direction, so that was good. Also, this row here is more like the density matrix that we saw from previous things last week. From there, once we have this partial density of our conduction band and our valence band, we have the difference of those to get our total charge density. We multiply that by the Coulomb electron charge, I think, and then we get our then we have the charge distribution that we'll put into our continuity equation. So once we have that, we can continue to simplify our equation, since the current density, which I believe Mira will be talking about next, it's a three-dimensional vector quantity. It has an X, Y, and Z component. Since we've made the choice to focus on the Z components, we can just say, all right, we'll just assume the average current density in the X and Y direction is 0. So when we do that, we can just focus on the Z part. We integrate it. We get this expression for the current density, and from there, we can implement it into mathematical code. So there's a file available on NERSC that was created by Dr. Johan, and for it, you need the energy pop file, the URL file, and backed out just like we did from last week. Basic calculations. As a note, the current version of the file assumes you have 600 time steps. I had to do some manual manipulation to the code itself since I didn't have 600 time steps for the graphics and some of the logic. So just heads up about that if you use this file. But once you do get that going, you have some pretty similar inputs to last week's field dynamic observables for the initial hole, the initial electron, the homolumo, then the Z steps. There's also some in-code calculations. I'm still figuring out where everything says what it is in the code, but I think this is where the integration takes place. So once you do that, we do get a similar graph to last week. We get a relaxation. We can also see charge density as a function of time and space. Here on the right, I have the model I was doing using for my research, which is a genus particle with cadmium selenium and a lead selenium nanocrystal together. But here on the left, our holes are like blue, electrons are yellow. We can have graphs for our charge density, the time derivative of the charge density, and the change in the current, respectively. So this is the graph from earlier, and I think a note here is the time derivative tells us that yes, there's some change taking place at some point in time. There's also another simplified graph which just shows the current density changing as a function of time. And here this line's just added in to say where the charge is 0, so you can see like where it's changing around. So guess that's my presentation on the continuity equation using it. I'll leave it open to questions.
Yeah. Let's thank Hadassah.
I have a question.
Go ahead.
I know you said you specifically chose the Z direction. Do you know why that is?
The way I set up my model, this year it's oriented with respect to the Z direction. I was specifically exploring just a spatial separation with respect to Z. So I was expecting the charge to, and also previous research I've done shows this charge transfer between going in the Z direction. Does that answer your question?
Yes, it does. Thank you.
And Hadassah, if I'm not wrong, that divergence operator is just applied in the Z direction. So, and code also is working just assuming that you want to have your plot just in the Z direction. It doesn't work for other direction. Otherwise, you should just tweak the code if you want to, for instance, have a model stretch in the Y or X direction.
What was that again in here?
I'm saying that your initial structure for these codes, usually you should have the codes are developed based on this assumption that you want to plot the distribution of the charges just in the Z direction. So if you have a different orientation in your chemical structure, you just need to tweak a little the code. By the way, thank you. I think you didn't get what am I talking about.
I guess, are you saying it looks like what I have in the code is different than what I have for my model?
No. For instance, your model right now is in the Z direction. It's okay. But if it was a stretch in the Y direction, so that was not consistent with the current version of the codes. So that's the only thing that I'm talking about.
Okay.
Maybe why you choose what G direction, why you don't choose an objection or
It was just how I chose to separate things. I just decided to separate things in the Z direction, and then it also worked out that that's how these integration things work out.
why did you decide to see what why not index and why the structure maybe straight instead of G?
I don't know. I just have them spatially oriented with respect to C. So, and I was just interested in the charge transfer between the two. So, it's just how they were set up. I suppose if I set it up in another way, I could just rotate the model as needed for this calculation.
You go a couple slides back for more, a little more. That's before the color. Yeah. Could you go over why you could say that we can drop our X and Y terms?
I think in part we're focusing on the distribution with respect to the Z-axis. So I guess while we're mainly interested in Z, otherwise I'm not completely sure why the assumption's made that you can just average the current density in the X and Y direction.
For this, I guess, going from your first to the second, one that required those derivatives to be constant. For this to be true, assuming that Jx only depends on X, Jy only depends on Y.
Yeah.
You have any motion of charge in Y and X direction, or it is only in Z?
I guess since there's molecular dynamics going on, it's possible that there's X and Y motion, but maybe it averages out, so it's negligible.
Okay.
So if we take it as an approximation so that there is a cube or cylinder and things go on in z direction. So current density in x and y do not change over. So there is just the zero.
Okay. That makes sense.
A provocative question toward the second part of today's talks. When the model is mostly emissive, when it is right after it is being excited, at the process when it transfers charge, or like, can you comment? Will your model ever emit light or something you prevent it from emitting light?
I guess it depends on, well, it's the charge transfers motion of the electrons going from one band to the other. As long as there's some charge transfer occurring, I'd expect there to be some emission of light.
So emission is facilitated or suppressed when you do the charge transfer?
Facilitated.
Or suppressed? Because to recombine, they need to immediately merge together, right? They don't pull apart from each other. They at least are expected to have low oscillator strengths and be not very emissive.
They're
If they're physically separated in space, there is their ability to recombine and emit light should be otherwise. Okay?
Yeah.
So this is the connection between first and second chapter, and the assessing spectral signals of these structures is indirect measure of charge transfer. Depending on how much charge is being transferred, it is more or less object related.
so more charge transfer means less
It will
object.
be darker. It will be darker.
Okay.